In this video, we're going to do even more with our integrals, another application where we find the center of gravity or a centroid of an object. So first, let's just define the type of object we're going to talk about in this video. So we're going to consider an idealized flat object. That is thin enough to be viewed as a 2D plane region. Called a lamina. And so you can think of this kind of like a very, very thin piece of paper. You can think of it as two-dimensional. It doesn't have to be rectangular like a piece of paper, but some very, very flat object that is very, very thin. And in this particular video and class, we are going to consider what are called homogeneous lamina. And homogeneous lamina are just ones whose composition is uniform throughout the whole object. So the density of a homogeneous lamina is its mass per unit area. So we denote the density by delta. This is a lowercase delta. They're pretty strange looking, kind of like a lowercase d, but wigglier. So this delta equals my mass divided by my area. Or in other words, my mass is equal to this density times the area. So we are going to assume that the acceleration due to the force of gravity is going to be constant. Assume the acceleration due to gravity is constant and that the lamina occupies a region R in the horizontal XY plane. So by horizontal XY plane, I'm just talking about, think of your normal coordinate grid, but instead of picturing it up on the wall here, it's laying flat on the table. So we have our lamina is just something laying flat, and our gravity is constant. Then there exists a unique point which we call X bar, Y bar, such that the effect of gravity on the lamina is equivalent to that of a single force acting on that point. This point, x bar, y bar, is the center of gravity of the lamina. So this sounds really, really complicated, but what you can think of it as is picture this flat, thin object. We're saying there is a particular point on that object where you could balance it on the tip of a pencil. That's all it's saying, and that point where it can balance perfectly without tipping over in any way, that point is called the center of gravity. So we have to figure out a formula to find the center of gravity, and it's going to be pretty complicated to get there. So hang in there a little bit longer while we set up the theory before we get to the examples. So the tendency for the mass m at a point to produce a rotation of a sheet about the line x equals a is m times x minus a. And it's called the moment of m about x equals a. So what this is saying here is picture, we were just talking about the center of gravity, a point where it balances perfectly. This is talking about if you were trying to balance your lamina, pretend this is thin enough to be a lamina, trying to balance it on a point, the tendency of the mass to rotate over in a particular direction is given by this formula, and it's called the moment. And similarly, the moment of m about y equals c is m times y minus c. So why do we care about these moments? Well, because our lamina will balance on like a knife edge along those lines if the sum of all the moments of all of those points happens to equal 0. So the plane will balance on a knife edge along x equals a if the sum of the moments about the line is 0. And this is similar for y equals c. Now, why do we care about where it's going to balance along a knife edge? Well, because the center of gravity is going to be right along the intersection of those knife edges. So I'm going to skip actually some of the theory because we've done so much of this theory so far in this class. But through our usual theory of cutting into strips and summing and taking limits, we get formulas for these moments. The first moment of the lamina bounded by y equals f of x about the y-axis is given by my, which is the integral from a to b of delta, or density, times x times f of x dx. And the first moment about the y-axis, about the x-axis, is mx, which is the integral from a to b of 1/2 delta times f of x squared. So those are our two formulas for the moments of the lamina about the y and x axis. And now we can finally define our center of gravity. Our center of gravity, x bar, y bar, is given by x bar equals my over m, and y bar equals mx over m, where m happens to be the mass of our region R. Which is the integral from a to b of delta times f of x dx. Now, these are pretty complicated formulas, so the two formulas I just erased for mx and my are used in the formula for this centroid, or center of gravity. So I have to have one of those integrals divided by this integral, and the other integral divided by this integral. Lots of integration going on. Now, note that if our lamina is homogeneous, which is the only type we're working with in this particular class, then the density ends up being constant. And that means that these deltas in the formulas end up canceling out. So the formulas I just gave you here were a general case, but if the lamina is homogeneous, which all of ours will be, then the center of gravity is called the centroid. And x bar equals 1 over the area of R times the integral from a to b of x f of x dx. And y bar is equal to 1 over the area of R, integral from a to b of 1/2 f of x squared dx. So these are the formulas that you're really going to need. Now, those formulas right there are the same ones that we just had with the mx and my. It's just that the deltas have canceled out. So this is equivalent. You can memorize it either way, but you will need to know that. So let's go ahead and do an example using these formulas. Let's find the centroid. Of the semicircular region R that I'm going to draw right here. Now, pretend that that's actually a perfect semicircle. This is my region R. And we want to find the centroid of this region R. Now remember, the centroid is the place where if this were laying horizontally, we could balance it on the tip of our pencil and it's not going to flop over in any particular way. And that's going to be where the balancing along a knife edge in the vertical or horizontal direction ends up being, the same. They intersect each other. So we can actually save us a little bit of time. Take a look at this picture. Imagine this being flat and picture trying to balance it on a knife. Is there any place where this already very clearly balances? Yeah, this y-axis. If you picture this being flat, balancing it horizontally on a knife, you could put a knife right along this y-axis and it's perfectly balanced on both sides and it can stay balanced. So what we have, since our y-axis is a line of balance, this means that the x-coordinate of my centroid has to be 0 because my centroid is going to lie somewhere along that y-axis. I just don't know exactly where, but I know it's somewhere along this vertical line. So I know my x bar is equal to 0. Now we could have gotten that x bar by using the formula as well, but it takes a long time. So let's just go ahead and find our y bar using that formula. In our next example, we'll end up using the formula on both, I believe. Let me double check. Yes, we used the formula for both on our next example, so we're going to save time on this one. So, take a look at this semicircle here. What's the equation of the semicircle? Well, I know that the whole circle would be equal to an x squared plus y squared equals an a squared because my radius is a. And if I just take the upper half of that, I get my f of x is equal to the square root of a squared minus x squared. This is found by taking x squared plus y squared equals a squared, solving it for y, which is our f of x, and only taking the positive root because I'm above the x-axis. So there's my semicircle, and now we're going to find our y bar. My y bar is equal to 1 over the area of our r times the integral from an a to b, which in this problem is negative a to a, of 1/2 times my function squared with respect to x. And my function is the square root of a squared minus x squared. So again, this just comes from the formula for y bar, and I'm just plugging this function into the formula. So let's go ahead and try to calculate this. Well, you already see over here the square root and the squared cancel out, so that's super nice. And for that area of r, well, I just erased my picture, but it was a semicircle. A semicircle has area 1/2 pi times the radius squared, and my radius was a. So there's my area of r, integral from negative a to a of 1/2 a squared minus x squared dx. And so now I can pull this 1/2 outside, and it will cancel the 1/2 down in the denominator over here. And we just get 1 over pi a squared times the integral from negative a to a squared minus x squared dx. Now I can do my antiderivative. The antiderivative of the a squared is a squared x. And the antiderivative of x squared is 1/3 x to the 3rd. So I have 1 over pi a squared times a squared x minus 1/3 x to the 3rd, and we have to plug in a and negative a. So here's my 1 over pi a squared. When I plug in positive a, I'm getting a to the 3rd minus 1/3 a to the 3rd. And when I plug in the negative a and then subtract what I get, I'm going to end up getting a positive a to the third and minus a 1/3 a to the third. So when I combine all of that together, well, I'm going to go ahead and multiply some of this through. I have 1 over pi, and this would be a minus 1/3 a plus a minus 1/3 a. Just to make it a little easier, I multiply my 1 over a squared through to cancel out some of my a's. And then I combine all of that together, and I get 4 over 3 with a pi times my a. Now, what was this again? This is my y bar. That's the y coordinate of my centroid. So my centroid is the point 0 and 4 over 3 pi times a. That is the point where the semicircle will balance. It's the center of gravity or the centroid for that semicircle. And we got that just using that formula. Let's do another example. Well, before we actually get to the example, I want to make sure we are ready for it. Let's consider a homogeneous lamina that occupies the region R between two continuous functions f of x and g of x over the interval AB, where f of x is greater than or equal to g of x on the interval. So our lamina, instead of just being bounded by one curve, it's smushed in between two curves. But if we combine our knowledge from earlier in the class, finding the area between two curves, to combine that knowledge with our new knowledge of centroids, we get the version of the formula for centroid, where our region is between two curves, is given by these formulas here. Basically the same thing, except we're going to have an f minus a g. My x bar is 1 over the area, integral from a to b of x times f of x minus g of x dx. And the y bar is 1 over the area of R, integral from a to b of 1/2 times f of x squared minus g of x squared dx. So the area of R would be the integral from a to b of f minus g. We've done that before when we did area between two curves. And the only thing that changed in these formulas here is instead of just having an f of x up here, I'm going to have an f minus a g. And instead of having just f of x squared down here, we have the f squared minus the g squared. So let's do an example where we're finding the centroid of a region bounded by two different curves. Find the centroid of the region R enclosed between y equals x squared and y equals x plus 6. So let me draw a quick sketch of what this looks like. There's my x squared. We'll say that's x plus 6. And these 2 points where they intersect are -2, 4. And this point here is 3, 9. Now, you could have found those points yourself by setting the 2 equations equal to each other to see where they intersect. We've done that in plenty of other videos. I'm trying to save us that time. So here's the region R. And we want to find the centroid, the place where we can balance this on the tip of a pencil. So notice that in the formulas that I just erased, to find our centroid, we definitely need the area of our region. Now, in the last example, a region was just a nice semicircle, so I could figure out my area using geometry. On this one, we have to find the area using integration. So here's my region R, and we know how to find the area of it by doing the area between these 2 curves. So let's start by finding the area of R. We're going to have an integral from -2 to 3 of the top function minus the bottom function. So x plus 6 minus x squared dx. That's just finding the area between 2 curves, which we did back in the first video of our class. So now let's just go ahead and calculate this antiderivative so we can get the area of R. So again, my area of R was the integral from -2 to 3 of the top function minus the bottom function dx. And so I get a 1/2 x squared plus a 6x minus a 1/3 x to the 3rd, and plug in our bounds. And now I just need to plug in those bounds. If I plug in the 3, I'm going to get 9/2 plus 18 minus 1/3 times 27, that's minus 9. And now when I plug in the -2 and subtract the results, I get a -2, a +12, and a -8/3. If you get a common denominator and add all of those together, you will get 125/6 as the area of R. Now, we have to still find the centroid, which means we still have 2 more integrals to go. We have to find our x bar and our y bar, but we needed this area in order to find those. So let's write down what the formula for x bar is again. Your x bar is supposed to be 1 over the area of R times an integral from a to b of x times f of x minus g of x dx. So filling in our information, we just found that the area of R was 125/6. So 1 over that will be 6 over 125. We just flip it upside down. So I get x bar is 6 over 125 times my integral. My bounds are still -2 to 3, and I have my x. Now this f of x minus g of x, that's still top function minus bottom function. So that's x plus 6 minus x squared dx. Then I would distribute that x through to get an integral of x squared plus 6x minus x to the 3rd dx. And now we can do this antiderivative. So I'm going to have my 6 over 125. My antiderivative is 1/3 x to the 3rd plus 3x squared and minus 1/4 x to the 4th. And then I just need to plug in my bounds. Saving ourselves a little bit of the arithmetic, as long as you trust my arithmetic. I have 6 over 125 times, when I plug in 3, I'm going to get 9 plus 27 minus 81 over 4. And then when I plug in the negative 2 and subtract the results, I get positive 8/3 minus 12 and positive 4. And now I just have to combine all of that together in the parentheses. You would need a common denominator, and you will get 125 over 12. Well, that's super nice, because now my 125s cancel and I just get 6 over 12, which is 1/2. So are we finished yet? No. This right here is just the x-coordinate of my centroid. We still have to find the y-coordinate, but we found the x-coordinate at least, so I know that the centroid is somewhere where x is equal to 1/2. Let's go ahead and find y bar now. So y bar is equal to 1 over the area of R, integral from a to b of 1/2 f of x squared minus g of x squared dx. So remember, f was the top function and g was the bottom function. And we also know our area of R. Area of R was 125 over 6, so I flip it upside down and get 6 over 125. My bounds are still negative 2 to 3, and there's my 1/2. My f of x was my top function, x plus 6. My g of x is my bottom function, x squared. Now I can kick the 1/2 to the outside, making it 3 over 125, integral from negative 2 to 3, and do some distribution. I'm going to have an x squared plus a 12x plus a 36 and minus x to the 4th. And now I'm ready to do my antiderivative. So it's just all power rule again. Erase that. So I get 3 over 125 times my antiderivative, which is 1/3 x to the 3rd plus 6x squared plus 36x minus a 1/5 x to the 5th, evaluated at 3 and negative 2. Now if I plug in those numbers, we should get 9 plus 54 plus 108 minus 243 over 5 plus 8/3 minus 24 plus 72 and minus 32 over 5. Now I would just have to get a common denominator in there. It's going to be a common denominator of, well, you would have to do 15 and then simplify, and you will get our 3 over 125 is multiplied by 500 over 3, if you combine all that stuff together as one term. Now I just have to simplify this. My 3's cancel out. It's 500 over 125, which is 4. This guy right here is my y bar. Now are we finished? Yes, we have found our centroid. We just have to write our answer. This means that our centroid is the point. My x bar was 1/2, my y bar is 4, and that is the centroid of that particular region. Now, just so that we can see what's going on, let me quickly remind us what this region looked like. There's my x squared. I said this was x plus 6. This point here was negative 2, 4, and this point here was 3, 9, and we just said that the centroid of this region is going to be at 1/2, 4, which is approximately right about here. Does that look like that could be the center of that object? Yeah, it's reasonably in the middle of that object. Obviously, my graph is not to scale, but I wanted to show you exactly what this is calculating for us. It is calculating that point where I can balance this object on the tip of a pencil. So that is about it for us on finding the centroids of these various objects. Is it pretty complicated? Yeah, sort of. It's integrals that we can handle. It's just you have to do a lot of them to get to the end of the problem. So I would suggest that you make sure you have the formulas for x bar and y bar memorized, so that then it's just a matter of running through some integrals and you can find the centroids of the objects. If you have any questions, feel free to drop them below. If you're a current student of mine, you can also ask an email or in office hours. And I'll see you guys for our next video.